All right, so today we are taking a look at angular momentum. And like a lot of the topics in this chapter, we're going to kind of compare angular momentum to the momentum that we've seen in the past. And so the momentum that we've seen in the past was just simply this. So momentum equals object's mass times its velocity. That was the setup. Pretty easy, pretty straightforward to follow in terms of regular linear momentum. And so with this chapter, with like a lot of things, we're going to adapt this equation to angular quantities instead. Angular momentum has the variable of capital L, so there's something we got to get used to. And then that's going to equal, remember in this chapter, we're not just concerned with how much mass something has, but we're also concerned with where that mass is located at in relationship to the axis of rotation. And so that is the definition for, a lot of words I know, but that's the definition for this guy that we saw just a few days ago, which was rotational inertia, so capital I. And then we're not dealing with velocity in the linear sense, so we can't use a v. We're now dealing with velocity in the angular sense, so we use omega. So again, pretty straightforward. New characters to learn here. So we've got angular momentum is equal to an object's rotational inertia multiplied by its angular velocity. So that's the way this reads, but again, easy to manipulate this equation, rearrange it, whatever we might need to do. Just remember that this equation is going to expand out because looking at this right here, we got our I value. Our I value is going to change based on the object that's in the problem. And so we might have, if we have, let's say, like a ring or a hoop, then we might have an equation that looks like this where we're plugging in Mr. squared times omega. We might have a situation where we have a disk and we have 1/2 Mr. squared omega. And we might have something like a solid sphere where we have 2/5 Mr. squared omega. So we've got our base equation, but then from there it kind of expands out and expands out into these possibilities if we have ring or hoop or something like a mass on a string. Then we got our disk, and then we got our sphere. So just all things to keep in mind as you're kind of solving our way through some of these problems. From there, we can also look at impulse. If you remember impulse from when we dealt with linear momentum, impulse was just simply a change in momentum. So delta P, that's what impulse is, a change in momentum. And that equation was Ft, how much force gets applied, and for how long. So remember we had things like a hammer hitting, big amount of force, small amount of time, which would still lead to a big impulse, versus it might be something more subtle like pushing a cart with a slow and steady force, but for an extended period of time, where we could end up with kind of a bigger impulse overall. So we're going to adapt this equation as well. Up top here, we saw that momentum, angular momentum, is abbreviated with this L. So instead of delta P, we're now going to be looking at change in angular momentum. And to change this into angular quantities, we're not in this chapter worried about just the amount of force. We're also worried about where it's located at, where the force gets applied in relationship to a distance from the center of rotation. And so we called that torque. So we're going to have tau, and time is going to stay the same. So that is our impulse equation that's adapted to angular quantities. Remember that this part can expand out, so we may have something that looks like this, just depending on the scenario, where you actually have to do like a final minus initial to get your delta. That's also another way to solve for change in angular momentum, is to just do this part as well, because remember the delta L is the change in angular momentum. So this is what's kind of spelling out what to do for that step. So this is like the impulse. Okay, and then last thing to look at here is conservation of angular momentum. So I'm going to write that out, conservation angular momentum, and abbreviate that. Scoot that up so you can actually see it. For here, basically it's stated just like conservation of momentum. If you remember conservation of momentum, it was just simply mv equals mv. And sometimes you had more than one object where you might have something like this. and those got a little bit more complicated so that you'd have to kind of label out like what the objects were so you could pay careful attention to that. These problems are going to be basically the same kind of setup. You're going to start with this and then expand out if you have more than one object. Got to be careful with your I values based on whatever the rotational inertia is of the object. Is it a disk? Is it a sphere? Is it a ring? That sort of thing. Good conceptual stuff that we can look at, and we will in class and look at some videos, but just to kind of explain a little bit of that now, you have like a figure skater, and figure skater has some kind of rotational inertia value and is spinning. So we'll talk about kind of the spinning of the figure skater. Figure skater can actually manipulate this I value, this rotational inertia. And if you think about it, if figure skater is standing, all right, here, I'll try to draw this out. If figure skater, here's figure skater, having a good time with crazy hair. Figure skater is spinning, and you notice figure skater's arms are outstretched. Then, here, I'll put some hands on there, kind of oversized hands. But you see that this mass is far from the axis of rotation. The axis of rotation is actually right down the middle of this, this figure skater, and all of this mass is kind of far away. So in this case, the I value, the rotational value, the rotational inertia value, is pretty high because they are putting a lot of their mass far away from their body. And so let's say that's the scenario here to start. As we get over to the second part, I'm going to write conservation law. What if the figure skater, I'm not sure exactly how I'm going to draw this, but I'm going to give it a try, does this instead? Give them some eyes and some crazy hair again. And you notice they're holding their hands, I'll explain this, they're holding their hands close to them, close to that center of rotation, that axis of rotation. And by doing that, they have actually lowered this I value. So here you have a situation where that went down, because now the mass is closer to the center of rotation. And conservation law says whatever angular momentum we have on this side, we have to account for that over here. And if the figure skater is going to move that mass closer to the axis of rotation, rotational inertia goes down, which means over here, the only thing that can change to keep our values the same is to have that angular velocity go up. That's the only way to maintain whatever number we have here in terms of angular momentum over here, is to compensate. And so when you see this, and I think everybody's seen it, when figure skater tucks their arms in, they're going to speed up. And it's not that they're applying any extra force or anything like that. They are just lowering their rotational inertia value, which means their speed's going to go up. When you see figure skater want to slow down, so they do this, they go crazy and spin, spin, spin. When you see them want to slow down, they go right back to this. They raise their rotational inertia value and they slow down. So that's some of the conceptual tie-ins that we'll see with this law, as well as the mathematical.